Hello everyone, myself Soiko, and today I am going to discuss about carbocations. So basically carbocation is a reactive intermediate species. So what is reactive intermediate? Reactive intermediate are those species, those are formed in between a reaction, and those are highly reactive and short-lived species, like their lifetime is less than a second. So that's why it's very difficult to isolate them. So there are several reaction intermediate available, but today I am going to discuss about specifically carbocations. So what is carbocation? So carbocation is a compound that contains positive charge on a carbon atom, and the carbon atom is sp2 hybridized. So obviously the geometry will be trigonal planar, and it's 6 valence electron. So it acts as an electrophile. Now what is electrophile? So in electrophile, electro means electron and phile means lover. That is electron lover. Obviously, since it is a 6 electron species, it's electron deficient species. So obviously it can act as an electron or a phile. So to gain its to fulfill its octet, it needs to accept the electrons. Now again, it is highly reactive and it is hot-lived species. So there are several reactions in which carbocation is formed as a reaction intermediate. For example, in ethanol reaction. In ethanol reaction, we have carbocation as a reaction intermediate. So these are the properties. Now I am going to discuss about the formation. There are basically two ways in which carbocation can be formed. So the next topic is formation. The first one is catalysis. Let's take an example to understand this. Let's say we have this alkyl iodide. Now this carbon iodide bond can break hydrolytically and generate a carbocation. So this is the one way to generate carbocation. This is hydrolysis. Now the other one is electrophilic addition. The other one is electrophilic addition to carbon-carbon molecule bonds. Let's take an example. Let's say we have this type of compound and we add HBr to this. So the carbon-carbon double bond will break like this, except this proton, and generate a carbocation. Right? So these are the two ways in which we can form carbocation. The first one is hydrolysis and the second one is electrophilic addition to carbon-carbon molecule bonds. Now we will see the classifications of carbocation. So next is classification. So the first one is alkyl carbocations, or that is alkyl. So basically when carbon atom, that is carbon atom is attached with a normal alkyl group, it is a alkyl carbocation. Let's take some examples like this. This is a 3 degree carbocation because the carbon having positive charge is attached with 3 carbon atoms. So it is a 3 degree carbocation. This is 2 degree because the carbon having positive charge is directly attached with 2 carbon atoms. Now if it is attached with only 1 carbon atom, then it will be 1 degree or primary. The last one is this. That is methyl carbocation. In this case, the carbon having positive charge doesn't have any alkyl group, so it's a methyl carbocation. So the other classifications are like we have allylic carbocation. What is this? This is like when the carbon having positive charge is attached with a adjacent double bond, like it is adjacent to a double bond, so it can undergo resonance. So this is allylic carbocation. And the third one is vinyl. In vinyl carbocation, the carbon is attached with another carbon via a double bond. So it is a part of that allyl, like alkene. So it is a vinyl carbocation and it is a allylic carbocation. So the other classifications are fourth one is aryl. So the fourth one is aryl carbocation. let's take an example to understand this. This is an aryl carbocation. So the carbon having positive charge is a part of a benzene ring. Then we will call it as aryl carbocation. And the fifth one is benzylic carbocation. In benzylic carbocation, what it is that the carbon having positive charge is adjacent to a benzene. So then it will be benzylic carbocation. This is aryl. The carbon is part of that benzene ring. But in this case, the carbon having positive charge is adjacent to a benzene ring. So it is a benzylic carbocation and this is the aryl carbocation. So these are the basic classifications of carbocation. Now we will understand the stability of carbocations. So why we need to bother about stability of carbocations? See, there are several reactions. Those reactions, the rate of those reactions are basically depend upon the stability of carbocation, like ethanol reaction itself. So we need to know about the stability of carbocations. So the next topic is stability. Now there are several electronic factors available. Those define the stability of carbocations. So now we also need to know that the order of those electronic effects, how they stabilize the carbocation. So the order of those electronic effects are: first is aromatic, then mesomeric, then resonance, then we have hyperconjugation, and the last one is inductive effect. So these are the electronic effects. Those define the stability of carbocation. First aromatic, then mesomeric, resonance, hyperconjugation, and inductive effect. Let's take some example to understand this. The first one is aromatic. Let's say we have this compound. This is a carbocation which is highly stable because it is aromatic compound. In case of mesomeric, we can have this type of carbocation when the carbocation is adjacent to a group which has plus N effect. Now, oxygen has lone pair of electrons. It can donate to the vacant orbital of the carbocation. So it will become although it contains positive charge of oxygen, it is highly stable because both carbon and oxygen atom have octet complete. Like when we can have positive charge on electronegative atoms when they have their octet complete. That's why, because this oxygen atom has octet complete, so it can have positive charge on it. Now, other electronic effects are resonance, like this compound. In this compound, this pi electron can be delocalized like this. This is the resulting structure. In case of resonance, when we are dealing with the resonance, so the stability of carbocation is directly proportional to the number of resonating structures. In case of resonance, remember this, that stability of carbocation is directly proportional to the number of resonating structures. Like in this case, we have two resonating structures. So if a carbocation has greater number of resonating structures, the stability will be even greater. And the next one is hyperconjugation. Let's one example to understand. Hyperconjugation, we all know that it's a no-bond resonance. We can call it a no-bond resonance. So the carbon atom adjacent to the carbocation is called alpha carbon. It has 3 hydrogen to 3 alpha hydrogen. Okay. Now you can go like this and we will generate C2H2. Okay. So in this case, like in case of hyperconjugation also, the stability is directly proportional to the number of alpha hydrogen. As you see earlier, that in case of resonance, the stability is directly proportional to the number of resonating structures. In case of hyperconjugation also, the stability is directly proportional to the number of alpha hydrogen. So the last electronic effect is inductive effect. So this is a general trend of this 3 degree more stable than 2 degree, then 1 degree, and then this. tertiary carbocation, this is 2 degree or secondary carbocation, this is 1 degree or primary carbocation, and this is we all know that methyl carbocation. So this is the basic trend in case of alkyl carbocation, 3 degree, 2 degree, 1 degree, and methyl, because we can see that there is 3 methyl groups present here. So this methyl group can show plus I effect through this sigma bonds, so the stability will be greater. There are 2 methyl groups, 1 methyl, so there is no methyl group. So these are the electronic factors that define the stability of carbocations. Now we need to also understand that how we are going to use these effects to compare the stability of carbocations. For that I am going to discuss about some questions. So the concept will be even clear. Let's take some questions. First question. Let's say we have this, then this carbocation. The third one is this. Now we have to arrange these 3 compounds on the basis of their stability order. How to do that? Now let's apply whatever we have learned so far. In this case, we can see that this is a 2 degree carbocation because it is attached with 2 carbon atoms. Again, it has 6 alpha hydrogen, right? 6 alpha hydrogen. Now the second compound. Right now, I showed you that in this case we have mesomeric effect plus n of oxygen. So we have mesomeric. Again, in this case, this is also 2 degree carbocation, but the difference is this. In this case, we have 6 alpha hydrogen, but in this case, we have 5 alpha hydrogens. Now, this only can't take part in this mesomeric effect because this is 1 carbon arranged from the carbocation. So, mesomeric effect is not possible. Okay. Now, then what will be the stability order now? So, we know that what is the order of electronic effects? Aromatic, then mesomeric, then resonance, hyperconjugation, and inductive effect. Let's see that here mesomeric present in this second compound. So the second compound will be more stable among these 3. Now how to define the stability among these 2? Between these 2 we can see that it has 6 alpha hydrogen, it has 5 alpha hydrogen. I mentioned earlier that the stability is directly proportional to the number of alpha hydrogens. So it will be more stable. 1. And then here compound 3. So this is the stability order. Second, then first, then third. Let's take another example. Let's say, second question. Let's say we have a compound like this, and second one is like this. Let's show the picture here, and the other one is this. So among these 3, which one is more stable? We have to tell that. Now let's see. In this compound, we have resonance structure like this. We can draw it. So 2 relative structures are possible in this case. Now in the compound, second compound, we have this relative structure. Again, we have another relative structure like this. This pi electron can be localized like this. So we have another relative structure. So in the second compound, it has 3 relative structures. So the second compound is even more stable than the first one because again the stability is directly proportional to the number of resonating structures. So the second compound is even more stable. Let's see the third compound. Third compound we also have relative structure like this. This pi electron can be delocalized like this. So we have mu like this. Right? Again, this pi electron can be delocalized in this. So we have mu. Now, in this relative structure, we have OAE adjacent to that of carbocation. So obviously we have plus N, that is mesomeric effect. So we have another structure. Now you can see that among these 3 compounds, the greater number of relating structure is for the third one. Again, it also has mesomeric effect. So obviously the third one will be the most stable, then the second one, and then the first one. I hope this is clear. So this is the portion of carbocation I want to conclude it here. Thank you.